So let's move on to the last part of lecture 6, namely adversarial data. So this describes the situation when the support, or overall the distributions between P and Q, are quite different, often chosen in such a way such as to elicit an unexpected and often undesirable response. And in this context, we actually need to talk about adversarial invariance, because as it turns out, adversarial data to a large extent simply exploits invariance in the data that we have not used for training. And so if you will, anybody who generates adversarial data is just a really good detective to find additional invariance in the data that we can then use for our purposes any further. Okay, so this sounds really complex and abstract. In order to make things more concrete, let's look at something specific. So let's say I want to do celebrity recognition, and of course, everybody knows this face, and I work for Amazon, so this is of course Jeff Bezos. And yes, the system is very accurate. And as a matter of fact, down below, this gentleman there, right, that's our current CEO, Andy Jassy. And so if you want to use a celebrity recognition system, well, you want it to respond to it, even if, for instance, we dressed up Jeff Bezos nicely. So let's say I were to add some glasses. Okay, as you can clearly see, I'm not the designer, but if I were to add some glasses to his face, everybody would still say, yeah, that's still Jeff, right? And even if I were to do horrible things like add a mustache, well, which probably wouldn't suit him, but you would still say it's Jeff. So let's undo this very quickly. But regardless, such modifications shouldn't actually change things in any meaningful way. Now, as it turns out, there are some algorithms which are able to perform such modifications, which to humans look completely innocuous, but which can throw off a face recognition system very effectively. So for instance, there's a quite well-known paper from 2017 by Sharif et al. And what they did is they added, fake eyeglass silhouettes to a person. And then they made it so that therefore after that, the face recognizer recognized that person as some celebrity. And I forgot exactly who it was, but I think these eyeglasses made him look like Mila Jovovich or something like that. So you might say, okay, well, this is really cheating because this is just operating on the photo, and you surely cannot do this in real life. As it turns out, they actually went off to 3D print glasses and texture them appropriately, right? I mean, obviously in a different pattern than what I'm drawing here. But those glasses, which clearly shouldn't really change somebody's appearance, did that in the eyes or in the algorithm of a face recognition system. So what we learn from this is that in some cases, machine learning systems are easy to fool in ways that humans don't get fooled. Now you might say that's just images. Well, it turns out you can actually do the same thing for audio. So in a paper by Carlini and Wagner, 1 year later, they did the same thing for audio, where they added imperceptible noise to the audio. So this is basically 0.1% of the original signal. And they made it so that this perturbed signal now was recognized as a very different text rather than the Charles Dickens novel, right? So what this means is they actually set this up as a nice optimization problem. They said, well, they want to have a minimal perturbation delta. This is the original data. This is our classifier. And this is the loss. So this is completely standard. And they said, basically, let's find some perturbation delta, which is small. So in this case, for instance, less than 0.1% of the original signal, such that the perturbed data is recognized as something entirely different. For instance, something that is just very discrepant from the original input, or is very similar to another specific targeted input. So you can use adversarial data to make the system particularly bad, or you can make it misbehave in certain ways. This actually has nice security implications. So as it turns out, very recently, some bank in the Middle East got robbed by somebody synthesizing data cloned from some voice, namely the voice of the manager of that poor bank employee, ordering the employee to, well, transfer money. And this, to my knowledge, is one of the first adversarially synthetically generated audio signals that actually led to a bank robbery. In any case, well, you can clearly see that by picking different norms. So by picking the 1 norm, the infinity norm, the L2 norm, or some Fréchet norm or whatever, you can easily get, different solutions. And people actually wrote different papers for different norms, data sets, and loss functions and objectives. So this is a very fertile, albeit sometimes slightly boring, way of producing new papers by just taking an existing setting and changing one component and rerunning the machinery again. But it's a really good way for you to get started and to practice how to do certain things by, starting with an existing model and then varying pieces. But it's maybe not the most exciting paper that you will ever write in your life. Okay. But why does this actually work? Well, let's just actually look at it again in the context of cats. So let's say, this is our training data and not just training data, but also natural test data. So they live on some fairly small subset, some fairly small manifold on the space of all the images. And the goal is now to find some data that is slightly off that support. So we don't necessarily need anything here, but we probably want to have something maybe nearby here. And then you want to find that slight deviation such that the estimator applied to that slight deviation behaves very differently. And that's exactly what we have here. So here's, for instance, our cat in the lab coat. And while it's still a cat, it's a very unnatural one, because in real life, cats don't wear lab coats, right? Only lab rats do. Okay, fine, bad joke. But basically, what happens here is that, yeah, it's still a cat, but it's not a natural image. And so therefore, we may very well then, if you use that for an object classification system, this may very well classify this cat as a doctor. So you might say, well, this is really breathtaking, and is this really new, right? Because at some point adversarial data was all the rage, and you couldn't avoid going to conferences without seeing papers on it. Well, actually it's not. So everybody's, as a matter of fact, probably encountered this problem today. So essentially, if you ever checked your email today, you would have probably seen some spam email. And so what happens is that basically you have this constant arms race between the mail host that extends the data set and trains a new classifier in such a way as to retain the invariance, but also to distinguish between the unnatural perturbations and the natural ones. And so basically the spammer then, spammer's emails are rejected, and then the spammer finds a modification of that data set that succeeds. And obviously the point is that you want to find a perturbation such that to a human who reads that email, it still appears as if this is natural, and so this may have a higher chance of actually getting a response, whereas it's very obviously adversarially generated and it's clearly spammy. So for instance, really early attacks on spam filters added highly scoring words, and this worked really well when these spam filters were naive Bayes spam filters. So remember, in this case what we had is that P of y given x was proportional to the product over all I, P of xi given y times, of course, p of y. And so you naively assume that all features are independent. Now, this is clearly not the case, but if you make that assumption, then you get, some very quick and easy to train classifier. I would not recommend that you use it, but once upon a time, this used to be a quick and easily implementable solution for a software engineer. Now, ways to attack it are obviously, you add highly scoring words. The next advance was then to add highly scoring sentences. Then you can go and change and forge the header of an email. And one thing that usually is a good indication that the email is meant for me is it starts with Dear Alex. If an email starts with Dear Customer, we have found that the insurance for your vehicle has expired. Would you like to extend the insurance from your vehicle by the manufacturer? Then unfortunately, we still have to listen to that nonsense by phone calls, but at least in emails, that's by now removed. But essentially, the spammer attacks it by creating slightly deviating text, which still looks like the real thing, and then the spam defense goes and modifies and retrains the models. Now, let's compare that to invariances. So this is actually very old. So here's a rather famous and ingenious idea. It's not the oldest use of invariances, but I just want to illustrate that this is quite old, over 25 years. So invariance transforms, and that's the idea of it, don't really change the label. So therefore, okay, if this is maybe my data point, then since an invariance transform, such as this one here, does not change the label, I can look on the manifold of those invariance transforms, and then I can say, if I want to perform a query relative to that point to that manifold, or if I want to perform a query rather relative to this point, so if here's another point here, then I do not compute this distance, but instead of that, I go and compute the distance to the manifold, and this is then what's called tangent distance. And it turns out that this type of symmetry and invariance led to highly accurate classifiers. As a matter of fact, this was one of the record holders on the USPS handwritten character recognition dataset challenges for a while. And what's displayed here are, the scaling and rotation, axis deformation, diagonal, and thickness transforms. Then this is basically the derivative of that transformation. So it's basically it's actually a finite difference between the original and the transform. And these are the corresponding flow fields. And you can clearly see, for instance, that for rotation, right, the flow field goes like so. Whereas for scaling, it clearly, pinches everything together and so on. So this is actually rather nice because we can now use this vector field to then instantiate exactly, this tangent plane. After all, each of those vectors is, for instance, one of these terms. And then you just project on it. So it's using invariances for good. There's another rather famous paper, namely on virtual support vector machines by Bernard Schellkopf in 1997. And the main algorithmic innovation was that he managed to make this optimization work when computers had maybe 16 to 32 megabytes, not gigabytes of memory. And so he only had to add virtual examples when they were close to the margin, and otherwise he didn't have to do that. By now, this is actually pretty much standard. So for ImageNet, for instance, pretty much every paper adds invariants. So to crop and scale and change the mean and per channel and all of that. So this is actually a very straightforward thing. And, I'll walk you through a few examples. In speech recognition, you could, for instance, add background noise. You can add scenes. As a matter of fact, even when you record live audio, you may sometimes go and play back some background scene data to the speaker, because that actually confuses them a little bit and they speak more slowly, more loudly, more deliberately, and so on. So this way you can actually capture much more nicely the various variations in natural speech. Or for instance, in document analysis, you can remove random substrings, you remove words, you insert some. And in all of those cases, well, you can argue the overall meaning of the document typically has not been butchered. I mean, of course, if the sentence is like I do or I don't, then that would not be so great, but in general, it's invariant. And so this actually works quite nicely. So let's look at what this looks like in the case of cats. So we again perform cat torture here. Well, just virtual cat torture on images by taking that wonderful tiger cat and cutting it up into pieces like so. This would be, for instance, the first part, and here that's the second piece. And then of course you can, it's this cat here. Now you can, of course, and here's a tail and another leg. That's this piece here. Anyway, so you can make it darker, and you can turn this tiger cat into a gray cat, a yellow cat, an orange cat, and some bluish shaded cat. And in all of those cases, they're still cats. You can even go and then flip and do a lot of other operations. And as you do this, you now have a much larger augmented data set that has a lot of invariants included. And so then you can use this larger data set to perform classification. Basically, you train on that. And this way you get smoothness according to the changes that really shouldn't matter. This way, rather than 1 million observations, you get maybe 100 million virtual observations with much better accuracy. Now, one thing to keep in mind is that not all transforms are always possible. For instance, if we flip this lovely cat from the left to right, well, this is still okay, right? But on the other hand, if we turn this cat upside down, that's also a flip, then that poor kitten, unless it's extremely frightened, would probably not be hanging off the meshed roof. Oh no, that's actually a keyboard, so it definitely wouldn't be able to hang on to a keyboard being held upside down. So it's clear that not all transformations always make sense. Likewise, if I, for instance, have the letter 6 and I rotate it, then I get the letter 9. So that also doesn't make any sense. But for instance, for the letter 1, I can rotate it, it's fine. So for some letters it works and for some it doesn't. And you may very well use this label-dependent invariance to further augment your data set. Okay, so you can also crop, you can pick a sort of kind of random aspect ratio, you pick a random area size and a random position, and you go for it. And there we have all of our kittens. You can change the color, right? So there's a green cat, and there's a lot more. So there are a couple of libraries that you might want to remember. Probably the most important one in this context would be Augmentations. And Augmentations has a large list of such transforms readily available that you just throw at the problem and it's gone. Now you might ask, is there maybe a slightly more systematic way to fix this? And it turns out that there is. So there's a paper that we wrote in 2005, and unfortunately we didn't republish it 15 years later or 10 years later. Basically, what we did is, so this is Junhoi Teo, Sam Roweis, Amir Globerson, and we looked at a loss function and we said that, well, we want to transform the input. Okay, this is some transform. And then what we do is we penalize the loss according to the extent of the transform. So if the transform completely, perturbs the image. Let's say if you want to make it robust to noise, and if the transform is such that only 10% of all pixels are remaining and the rest is a complete mess, then we should probably be very generous and not assume that our classifier will do a good job, with high accuracy. Whereas if the transform is only very tiny, this function eta of delta is small. So what you would probably want to have is, if this is, the magnitude of delta, and this is eta, that this function probably looks something like so. Right, so with the magnitude of the transform, you have to pay less. In magnitude, with that I mean how disfiguring that transform is relative to the rest. And the good thing is you can basically generate that worst transform every time you see an observation, and then you take an update step relative to that, and this way you also get good results. So key takeaways. We call something an invariance if we know that the transformation keeps the outcome unchanged, and we add it to the dataset to make the model more robust. In adversarial data, we don't know that the transformation should keep the outcome unchanged, and so using adversarial data typically changes the outcome, and one way to defend against it is by treating it as an invariance. So let me give you an example of particularly malicious adversarial data. So I guess everybody knows Highway 101, and there's this highway, and basically there's at some point an overpass. So this is Highway 101. There's an overpass that leads to Highway 85. It's for the HOV lane. And what happened is, about maybe 2-3 years ago, and there's some gore zone that usually is meant to block things. So several years ago, a Tesla self-driving car was driving on one of those 2 lanes, and it ended up, for some reasons that are not entirely clear, within those 2 lanes. And I'm exaggerating a little bit here because those 2 lanes actually extended out quite a bit. And so now the poor Tesla found itself in a rather unpleasant adversarial situation where it had a solid line to its left, it had a solid line to its right, so these are solid lines, and there was no car in front of it, and it failed to recognize this gore zone, so it accelerated into the gore zone, very much to the detriment of the driver, who died instantaneously. And the car burst into flames. So this is an example where such adversarial data, even though it's constructed unintentionally, can lead to rather bad outcomes. If you ever take that highway, you can actually notice that by now, that entire zone here, they fixed that data source. They fixed it by adding crosshatches to it, such that should any other self-driving car find itself in front of the score zone, it will stop. Now, on a slightly lighter note, there's this joke of how do you catch a self-driving car? Well, it's very easy. You just draw a solid line around it, and it will never be able to escape. Okay, so let me conclude by that. I hope I showed you that there are at least quite some meaningful examples where the training and test distribution change. And then if this support of the distribution in the worst case changes, or you pick something that's a very low density region, then you can often get results that are highly undesirable and very different from what you would have wanted. And so this is probably one of the most important cases that you need to worry about if you, for instance, build anything that's security relevant. So for instance, if you use the face recognition on your fancy new iPhone to make sure that your bank account data is safe, then you're implicitly relying on the talent of Apple's engineers to build a system that is fairly robust also against adversarial attacks, namely somebody else being an imposter of mine, maybe speaking with the same Bavarian accent or maybe making the same smile or frown, in the hopes that this will then, trick the face recognition system to unlock the device. Okay, and with that, we've concluded lecture number 6. We'll cover the rest next time.